Welcome. This week we'll be talking about processes on networks. What this will entail is understanding how the underlying structure can affect a process such as diffusion. So we'll do a little bit of review. This is pretty much what you did for your second homework assignment. We'll look at diffusion in Erdős-Rényi random graphs. We'll look at it in scale-free random graphs. And something you haven't done before, we'll look at diffusion in small world networks. But, what we've seen so far is simple diffusion. That is, anyone who's infected can infect any one of their neighbors with some probability. However, not all diffusion is that simple. For example, when individuals are looking to adopt a new product, it may not be sufficient that they see just one of their friends has made that purchase. Perhaps they want to see until several of their friends have done the same. It becomes even more complex once there are so-called network effects in these decisions. So for example, if you're trying to decide between two different chat clients, some of your friends are on one chat client, the others are on another, which one are you going to choose? And it depends on how many friends are on each and how good the product is. And we can add an additional wrinkle, which is that perhaps you don't have to choose. Perhaps you can use both chat clients. However, this comes at an additional cost. You can't remember which friend is on which network, or you have to learn how to use both of them, etc. And this leads to rather different product adoption dynamics. We'll talk briefly about collective action. This is, for example, individuals choosing whether or not to go out and protest. Each of them might have a given criterion depending on, I'll go out if at least 3 people, including myself, go. So if I see that if I can coordinate with 2 of my friends and we all go out, I will be happy protesting. But people might have different criteria, so how can you determine whether a protest is going to occur or not? We'll also talk about innovation. Now, you might have an idea of, the lone innovator, the lone person who works at their desk and scribbles some formulas and then comes up with a brilliant idea and doesn't need to really exchange ideas with anyone else. They just patent it and get rich. However, a lot of innovation actually happens through networks, and part of it is that you imitate, that you use things that others have developed that work and then perhaps improve upon them further. So how does the network topology affect the process of innovation? And finally, we'll look at kind of collective problem solving, where you need to do something, but your correct answer depends on what others' correct answer is. So let's get to it. First, we'll go back to diffusion in Erdős-Rényi random graphs. I'm going to set up the network. And here, the main parameter is the number of nodes in the network and the average degree. And what you can do is then adjust the average degree and set up the network. You can actually go from average degree of 2.5 to something like 5. And for now, I'm just going to say the infection rate is going to be 1. That is, if my neighbor is infected at a previous time step, they're going to infect me at the next time step. And I'm going to simply spread the infection. So here's step 1, 2, 3, 4. We can observe that. Now I'm going to lower it down to 2.5. I'm going to set up the network, and I'm going to do the same thing. 1, 2, 3, 4. Looks different, doesn't it? I can lower it further, maybe just average degree 1.1, just above the percolation threshold. And now if I do 1, 2, 3, 4, see what happens. So I think we're ready for our quiz question. So this is just a recap of what happened. And the quiz question is, when the density of the network increases, the diffusion in the network is, and your choices are faster, slower, unaffected. So hopefully what you concluded was that the denser the network, the faster the diffusion. So if the average degree is 5, in 4 time steps, you had a lot of the nodes infected. And furthermore, if the density of the network falls to a really low value and you're just at the percolation threshold or below, in fact, the disease or whatever it is may not spread at all because there's not enough connectivity. So even if it had infinite time, it would never break out of the little network fragment where it was located. So now let's consider the effect of diffusion in networks which occur because nodes are added over time. These are growing networks. And we're going to look at 2 situations, one in which there's preferential attachment, meaning that new nodes who join the network will preferentially attach to existing nodes that have high degree, are hubs, have lots of neighbors. In the second example, the network's going to be grown non-preferentially. That is, the new node is just going to pick one of the existing nodes at random. So let's see what that might look like. So here I will, let's see, we can first grow it non-preferentially. Let me just set that up again. And now I'm going to, I think, again, move the infection rate to 1 just to speed things along. And now I'm going to say take, let's see how many steps. 1, 2, 3, 4, 5. Okay, 5 steps, and I've infected some portion of the network. It's not too bad. Now I'm going to grow the network preferentially. I'm going to click Setup, and now I'm going to take the same number of steps. So I'm going to click Spread once. 1, 2, 3, 4, 5. I've basically managed to infect most of the network. So going back, just to make sure we know what we're doing, when nodes preferentially attach to high degree nodes, the diffusion over the network is faster, slower, or unaffected. Hopefully you figured out that it's faster when we have preferential attachment. And this is the same observation as always. That is, when you have hubs that are extremely well connected, what's going to happen is they're going to get rapidly infected, right? If any one of their many friends has the infection, they will pass it on to them. And next thing you know, now they can infect all of the rest of their neighbors who hadn't been infected before. So having having hubs in the network really does accelerate the spread of anything, disease, information, etc. within the network. As long as you have these simple rules, that is that with equal probability, here we'd set it to 1, anyone who's infected will infect their neighbor at per time period. Next, we turn to small world networks. If you remember from last week, what made a network a small world was a high degree of clustering, here accomplished by putting the nodes along a ring lattice such that each node is connected to its 4 closest neighbors, and then adding some shortcuts. And what these shortcuts are going to do are make the average shortest path small, close to that of a random graph, while still maintaining a high degree of clustering. So let's go to the NetLogo model for this, and I'm going to at first have no recovery. So in this model, a node is susceptible, and then once it's infected, it stays infected. So some diseases operate like this. Unfortunately, there's no cure. So once you're hosting that disease, you're a host. So we're going to set up the network, and we're going to infect 1, and we're going to allow the disease to spread. And here the speed is somewhat determined by this probability of infection. So I guess I could, well, let's just keep it right there at 0.24. And now we're going to allow it to spread. and you can see what's going on. And we can then add a little bit of rewiring probability. This might be all we need. And we're going to repeat the process. So we're going to allow it to spread. And this hopefully will allow you to answer the quiz question, which is, as the probability of rewiring increases, the speed with which the infection spreads, does it increase, decrease, or remain the same? So going back to NetLogo, so hopefully you saw that the infection can spread more rapidly if it can use the shortcuts that we gave it by rewiring the network. Now let's add this probability of recovery. And what this is going to do is, with some probability, an infected node is going to go back to being susceptible, which means that it doesn't currently carry the infection. It can't infect its neighbors, but it's ready to be infected again. So let's have no rewiring, and we're going to set up a network. And here's one infected node, and then we're going to try and see if this will spread. So we see the infection kind of growing slowly, and it's hanging in there. Oh, this is actually pretty suspenseful, but it dies out. Now let's try this with a little bit of rewiring, maybe 5%. And see what happens. Now, naturally, sometimes the disease will die out because the nodes recover before they can really infect a lot of others. So I might have to reinfect the network a few times to get what I'm after here. So I'm going to allow it to spread. This time it died out, so I'm going to try and reinfect, see what happens. So you should be seeing qualitatively a different behavior in the case of the presence of rewired edges versus the plain lattice. And I'll let you examine this more in the assignment. Even though it may not have seemed that way, so far we've only considered simple contagion. And by simple, I mean that if one of my friends is infected, that's enough for me to become infected as well. Of course, there are parameters, the probability per time period that my friend infects me, whether they'll recover before they have a chance to infect me, etc. But the main thing that makes it simple is that it's just between me and one of my friends. And this makes sense for things such as viruses that are diffusing, or even information that's diffusing. It's enough for one person to tell me a piece of information, and then I know it. On the other hand, there are other processes, for example, the adoption of certain behaviors, or the making of purchases, where you may want to consider what multiple of your friends are doing. So for example, say I'm an impressionable teenager in high school, and I see one of my friends wearing red pants. I'm not going to run out and buy red pants just because one of my friends did. I want to make sure that several of my friends are wearing red pants before I'm really convinced that that's the cool thing to do. And then I'll go ahead and do it. And as you might imagine, this has rather different dynamics. So let's go back to that small world topology and see what that does. So here I am in NetLogo. I have created a slightly smaller network so we can better see what's going on. And what we're going to do is we're going to do this complex contagion process on top of the network, where the rules are that a node will look around to its neighbors and it will adopt the behavior, that is, it'll become yellow, if it decides to buy red pants. And it will do so only if at least 2 of its friends have done this already. So to begin with, we're going to infect 2 neighboring nodes, because unless we do this, the infection is kind of dead from the get-go. So no one's going to buy red pants if only one node in the network has bought red pants, according to these rules. And now we're going to allow this red pant craze to spread. I'm going to reinfect a few times just so you can see what's going on. And I'd like you to pay attention to both what is the structure like, where the infection is stopped, and also is the infection successfully using the short range ties, the long range ties. So we can kind of let this run a little bit, and hopefully this is enough information. Otherwise, you're very welcome to play with the model yourself. So here is our question. Relative to the simple contagion process, the complex contagion process, is it better able to use shortcuts? Does it advance more rapidly through the network? And does it infect a greater number of nodes? Complex contagion, even though it has the name complex, in this case, it had a very simple rule. That is, it was a threshold model, and the threshold was just in terms of the number of your neighbors that have adopted a certain behavior. However, sometimes what you're really playing is a coordination game where you have two different choices and you're trying to decide between them. And as I said in the previous segment, this could be, for example, deciding between different online chat clients, and it depends on how many of your friends are using each of them. So it's not that two friends are using it, but are more friends using one versus the other? And also importantly, how good are those chat clients? So let's switch the context a bit and say we're still choosing between two things, and let's just call them basketball and soccer. And if a friend chooses to play basketball as well, so they're making choice A, I will get payoff A every time for each friend. And if my friends choose B, then I will get payoff B. And if, I just have one friend and they choose the opposite of what I chose, then my payoff is 0, right? I get no enjoyment if I want to play soccer and I can't play on my own and my friend only wants to play basketball. So let's see how this plays out. This node in the middle is trying to decide between playing basketball, which 3 of his friends play basketball, or playing soccer. 2 of his friends play soccer, but that's not the only variable, right? So sure, 3/5 of his network is basketball and 2/5 of his network is soccer, but there's also the question of which one of these sports he enjoys more. So how is he going to do this calculation, deciding between the two sports? Well, this is the formulation. He has D neighbors, or D friends, and a fraction P of them are going to play basketball. This is the 3/5, and 1 minus P fraction of them are going to play soccer. This is the 2/5. And if he chooses to play basketball, his payoff is the number of his friends who are playing basketball, which is just P times D, times A, which is the payoff he gets per each friend who plays basketball. Similarly for soccer, the payoff, if he were to choose to play soccer, the payoff would be 1 minus P times D, that's the number of friends who are playing soccer, times B, the payoff he gets, or the enjoyment he gets from playing soccer with each of them. So this means that he should choose A if P times D times A is greater than or equal to 1 minus P times D times B. These payoff from soccer and payoff from basketball. And you can reformulate this so that he will be playing basketball if the proportion of his friends playing basketball is greater than or equal to B, which is the payoff for soccer, divided by A plus B, kind of the sum of the payoffs for either choice. And there are 2 equilibria in this problem. The first is that everyone decides to play basketball, and what an equilibrium means is that no individual, given the current situation, would want to switch, right? Because if everyone's playing basketball, you would get 0 payoff from playing soccer because there are no other soccer players, so it's just not possible. You get payoff 0 from each of your friends because they're all playing basketball. Similarly, everyone could decide to play soccer, in which case no single individual would choose to play basketball instead. But what happens in between, right? You have these equilibria, which is that everyone's just doing one thing. But what if for some reason you had two of the nodes switch? There could be some external reason. So let's see a particular example. Let's say that the payoff for playing basketball with a friend is 3 and the payoff for playing soccer with a friend is 2. And we have the payoff, that means that the payoff for nodes who are both playing basketball is 3/2 as large as what they get if they both choose to play soccer. So you get like a 50%, greater payoff. And this also means that nodes will switch from soccer to basketball if at least 2/5 of their friends are not using A, are playing basketball. So it means that it can be a minority. It can be 2/5 of your friends who are playing so much more appealing than soccer that you will switch once you pass that threshold. So let's see how this cascade might occur. Suppose you have some devious company that comes in and says, we'll give you free shoes, branded with some basketball player's name, if you play basketball and you don't play soccer. And so these two nodes then start playing basketball. Now, this node is looking and it's finding that half of its friends, so 2 out of 4, are playing basketball. And since the threshold for switching over is 2/5, now this node as well is playing basketball. Now the quiz question is, can you figure out which node or nodes will switch to playing basketball next? Is it going to be just A, just B, just C, or some combination of these 3? Okay, hopefully you figured out that it was B who would switch next because it was looking at its 4 neighbors, 2 of whom had switched. Versus at that point, if you exclude B, A was looking at 3 neighbors, only one of which had switched to basketball, and so that's 1/3, which is less than 2/5. So it wasn't sufficient to flip either A or C was in a symmetric situation. But now that B has flipped, both A and C also find it favorable to switch to basketball. And so what you just saw was a cascade going through the network, even though it just started with 2 nodes changing their minds or having their minds changed for them, and then everyone goes ahead and switches to basketball, which presumably is good because it seems like the payoff for basketball in this fake scenario is higher than it is for soccer. There's a NetLogo app, which you will be exploring a little bit more in your assignment, that allows you to try different topologies. And what you'll be doing is allocating an initial opinion. Your nodes are going to be flipping a biased coin, deciding, actually I think it's an unbiased coin, so 50-50 whether they're red or they're blue. And then you can update their opinion according to these rules and these payoffs. And you can try this several times just to see how the structure plays out as to what the stable configuration is. That is, no individual node would like to switch given their current payoffs. There are, of course, implications for viral marketing. If you really can influence some subset of the nodes, whether by paying them off or giving them free product samples, which individuals would you want to pick? And so using the same app, you can kind of take turns if you find someone to play this with. Otherwise, you can kind of play against yourself if you like. So you can take turns selecting which nodes you initially infect, and then you can see how the uh, what the payoff is as far as how many individuals eventually adopt your product, whether it's red or blue. So you would select blue and say, I want to, well, now it's red's turn, and red says, well, I want to be right here. And blue might pick here. Oh, sorry, we did another red, no matter. And here is blue. And now we can do successive updates and just see how things play out. In this case, poor red did not choose very wisely. So the question is, what is the stable set of choices, and how might you optimally select your initial set such that you would maximize your influence within a network? So having seen several of these demonstrations, let's see if you've built up enough intuition to answer the following. What is the role of communities in complex contagion? Do they enable ideas to spread in the presence of thresholds? Or do they create isolated pockets of nodes within the network that are impervious to outside ideas? Or do they allow different opinions to take hold in different parts of the network? Hopefully you've realized that they actually do all three. In the first case, complex contagion means that you need to observe multiple of your neighbors doing some action, or that you're going to decide based on the fraction of your network that is doing one thing as opposed to the other. And for this, community structure is very crucial because it provides the dense linking around the ego, that is the node, that allows them to observe similar behavior among their friends. Similarly, though, it can create isolated pockets of nodes who are holding on to one opinion or one way of doing things because they're seeing that, well, most of their friends within the community are doing something one way, and it would just be too inefficient or too costly to switch to something that someone is bringing in from the outside. So on the one hand, it facilitates adoption within the community, but it makes it hard for new things to come into the community in the first place. It also then consequently allows different opinions to take hold in different parts of the network because each community may not independently, but it may seem as if though they independently can hold on to their beliefs. One last wrinkle that I would like to introduce, and this you can read about in the Easley and Kleinberg chapter 19, is that of bilingual nodes. Now, what are you talking about, Lotto? We haven't been talking about languages. Well, in this case, it might mean if you actually are bi-sporty. That is, you play basketball and you play soccer. Well, that's great then. You can play with everyone who plays basketball and with everyone who plays soccer. However, typically in these situations, there's some cost. So besides the actual cost of maybe needing a pair of cleats for soccer and a pair of basketball shoes for basketball, perhaps the cost is your time. You simply have to spend more time playing both sports, and you may not get as good as, if you weren't splitting your time between the two activities. So in this case, being bilingual comes with a cost. Similarly, the earlier example of instant messaging clients, just having the overhead of having two messaging clients open or setting up a single messaging client to talk with two different services, and then having to manage your identity on two different clients as well can be a hassle, right? So there's some cost, but you may very well be willing to pay that cost because it means that you can now interact with more parts of your network, even though they may have been making different decisions. So let's try this on a line. So switching back over to NetLogo, I'm going to turn off bilingual, and I'm going to, this is what you might first see when you do setup line, but if you just lay out, you'll see that it's a nice ring lattice, in fact. and we can allocate the opinion at random, and then we can update. So just observe what's going on. Let me allocate again, right? And so, great. So we have A is the payoff for playing blue, and in this case, the payoff for blue is higher than the payoff for red. Now I'm going to turn on bilingual, which means that a node can choose to be able to interact with both red and blue. However, it will have to pay this additional cost of 2. So I'm going to allocate the opinion, and then I'm going to update. And you can see several bilingual nodes cropping up where they would like to talk to someone who's red and someone who's blue. And now we can keep updating. So let's just do that again. So we have initially nodes using red and blue. Now we update. So see if you can answer this quiz question, which is, what does the presence of the bilingual nodes do? Does it help the superior solution to spread throughout the network? Or does it help inferior options to persist in the network? Or does it cause everyone in the network to eventually become bilingual? What you could have concluded from the demonstration in NetLogo, let me maybe go back to it, is that these bilingual nodes are allowing the inferior solution, that is red, to persist, versus when we didn't have bilingual nodes, everything turned blue eventually because it simply had the greater payoff. So bilingual nodes are good in that they bridge, but in the long run, they may keep the superior solution from really taking over in the network. One last type of complex contagion that we'll talk about, and that is collective action. So previously we talked about in complex contagion that you may wait for a couple of your friends to wear red pants, and then on subsequent days you might start wearing red pants as well. However, in some situations, you may want to coordinate ahead of time because that first person to show up to school in red pants may very well not have a very good time because people might ridicule them. On the other hand, if you and three of your friends all decide to show up to school in red pants, well, people can try and ridicule you, but you have strength in numbers and you can kind of hold together and be just fine. So another example of where this can crop up is in protests. If you go out and protest on your own, sure, you might feel silly if you're the only one holding up a sign, but also if, for example, you're protesting in against an oppressive regime, it may very well be dangerous. So there's strength in numbers. If you're one of many people protesting, then it's less likely that you'll get in trouble. So you may want to coordinate with your friends. So just to sum up, you want to coordinate so that you don't end up here being the lone protester and that instead you're with your friends and happily protesting. So in general, though, different people might have different thresholds. So here is a node who would go and protest only if 4 people or more in total would go. So he would need 3 other friends to say, yes, we're going to go protest, and then he would be happy going and protesting. However, he only has 2 friends, which means that he doesn't even have a chance of doing a coordination among 4. This node would go if 3 people in total would go. So he would go if this node and this node would go. However, we already know that this node would not go. Now this node in turn would go if just one other person went, because its threshold is 2, so it and a friend would happily go. But now this one isn't going because this one isn't going, and so nobody goes, and no one goes out and protests. In this network, on the other hand, you would get partial turnout. This node doesn't have a chance. It wants to coordinate with 3 other people, but it only has 1 friend, so yeah, they're not going to go out. But these three nodes each have this threshold of 3, and they're all talking to each other, and hence they'll all go and turn out. So see if you can answer this question about the network here. And what we're looking for is whether this network is going to mobilize, whether at least a fraction of the nodes will protest. In this last segment, what we'll cover are interactions over network topology that affect how the nodes are innovating and solving problems. As you might well imagine, networks play a crucial role in how agile organizations are, how adept they are at innovating, how adept they are at coordinating. And first, we'll look at innovation. And of course, as with everything else, we're going to look at a very simple model that we hope may represent some aspect of the real world. And this is the basic conundrum. When individuals are innovating, they can collaborate. On one extreme end of this, you have everyone in the same room brainstorming, and that can, mean that you can really rapidly get new ideas and prototypes, etc. But you also have a danger of groupthink, right, where everyone is starting to think the same thing, and it may not be the very best solution that they could have achieved. On the other extreme, you have, for example, you could have a network where no one is connected to anyone else, and everyone is working individually. You might well imagine that their progress would be very slow because they can't take advantage of what others have figured out. They basically have to figure out everything by themselves. On the other hand, many people independently working on a problem means that you have many diverse approaches to the same problem, and perhaps one of those approaches will be optimal. So in a network context, if we have most individuals in the room together communicating, the network might look something like this. Everyone is connected to everyone else. On the other hand, and this isn't quite the same thing. Here, this individual is not connected to anyone else, but here, individuals will only talk locally to a few colleagues. They won't be, broadcasting every solution throughout the company. So one way to model the problem space that these individuals are moving in is with Kaufman's NK model. You have an n-dimensional space, which just means you have a bit of a string of bits that is 0 and 1. So, for example, if you have a car, the first bit can be, is the car black or white? The second bit could be, is it a sedan or a station wagon? The third bit could be, does it have a powerful engine or a modest engine, etc. Right? So they're just trying to figure out what the best car could be, for example. And the K parameter describes the smoothness of the fitness landscape. That is, if you flip one of those bits, if you make it a sedan as opposed to a station wagon, is that completely going to change how well the car sells, or is it going to be pretty similar sales based on the fact that the other very many bits are the same, including the engine and the amount of room inside and automatic versus manual transmission, etc. So just another way of looking at this, if K is large, you have a very smooth landscape, and I can't really represent the n-dimensional space, so this is just roughly so that you can imagine what's going on. This means that there is some combination that's optimal, and if you tweak it a little bit, you'll just get a little ways away from that optimum. The more you tweak it, the further away you'll go. But what this also means is that it's fairly easy to find what the optimum is, right? So you flip the color from white to black, and whoop, here you are, you've gotten to a better solution, etc. It's not that, once you flip the color, the fitness might jump over here, right? If you've just flipped one bit, you're moving a little bit. On the other extreme, where k is small or k is 0, it means that precisely this unpredictability happens. You flip one bit, and all of a sudden you're in a completely, you have completely different fitness. So making it a station wagon instead of a sedan means that people hate it, for example. And then k medium means that there's some smoothness. So if you're here and you flip a bit, most likely you'll end up having somewhat similar fitness. Now, the general problem is that, so here the solution's easy to find because you're basically just doing hill climbing, right? You keep flipping bits until you get to the top, right? Over here, you just don't know, right? You might be up here. It doesn't tell you whether you're any closer to, say, the solution here. Because, if you flip a bit, you might end up, having vastly different fitness. So there's no way to really orient towards what is the ultimate goal. With this intermediate smoothness, it means that, you can make some progress and you can find a local optimum here, this peak in fitness, but this may mean that you're stuck, because if you just change one bit at a time, you try going down here, you think, oh no, that's not going to work. I better stay here, right? So it's not as easy as here, where basically if you continue climbing to the top, you're bound to find the global optimum. Here, you can climb, and find a pretty good solution, but miss that there was actually a better solution out here. So there are going to be some update rules for our network such that we can simulate the process of either innovating or imitating. So those are the two choices that each node has. So each node is going to start out with a random bit string, and it's going to do one of two things. If it notices that a node that it's connected to has a better solution, it's going to copy that solution. Otherwise, if none of its neighbors are doing any better, then it's going to flip a random bit and see how it does. So either it's going to imitate or it's going to innovate. I've set up a simple ring lattice, and each of the colors represents a different bit string, a different solution. And you can see that there's variation in the fitness of these different bit strings. The highest one is 0.662, and on average, the average fitness is something like 0.5. Now, what we're going to do is we're going to allow the nodes to update according to these rules. If one of their neighbors is doing better, they're going to copy that solution. Otherwise, they're going to innovate on their own. So we're going to let it run. And eventually, okay, right? So everyone has converged on the same solution, but this solution, you'll notice 0.764, is higher than the original maximum. So there was some innovation taking place, and at the end, all of the agents because it's agent-based modeling, but all of the nodes converged on the same solution. And you can see like everyone has the same fitness. Now let's see if we go to somewhat of an extreme here and add 1,000 additional edges. So this is what it's going to look like. It's going to look very dense. This time we have a best solution of 0.673, and we're going to let the nodes update again. And you can see almost instantaneously they all converged, but the value that they converged on, let's see if you can answer the quiz question. Relative to the regular lattice, the network with many additional random connections has on average slower convergence to a local optimum, smaller improvement in the best solution relative to the initial maximum, more oscillation between solutions. What you should have seen was that when you have many ties between the nodes, let's go back, they actually converged more quickly, but what they converged on was not as good because they didn't spend enough time innovating. So in the assignment, you'll be trying to find whether there's maybe a sweet spot for both innovation and for this quick convergence. The final problem that I'll address is that of graph coloring. There's a very simple application of this, which is to coloring adjacent countries on a map. The printer at some point only had a fixed number of colors that they could use, and they didn't want adjacent countries to have the same color, because then, for example, you might think that Sweden and Norway are the same color if they were both the same peach color. Right? So you might imagine that the nodes are countries and the edges are drawn between countries that share a border. So this was studied by Michael Kearns, who is teaching Coursera's Networked Life. So this is an ad actually for his class, but I feel safe doing that now that we're already in week 6 and hopefully already committed to my class. But they did this very neat experiment with human subjects. So they sat a bunch of students in a lab, and each of them was sitting in front of a computer. And they varied how much information they could have about what color the other students had chosen. So each student was a node, and they were either told, they were placed on some topology, and they were either told what colors their neighbors had, or they could actually see the colors and the topology for the whole network. And the question is, how quickly could they converge on a solution? And with human subjects, it turned out that more edges helped the graph coloring problem, it helped it be solved more quickly. But in scale-free networks, sometimes the presence of hubs actually made it more difficult. So I'll leave most of this for the assignment. But here you have, 2 adjacent nodes have the same color, so they need to fix that. And indeed, in the final solution, I'm not sure whether I'm pointing to the same one. Now, yes, I am. So one of them is green and one of them is blue. So they switched, and this one that was also blue switched to red. So here I have a small world topology. I can generate this a few times. I guess we have a very low rewiring probability. And to start off with, many neighboring nodes have the same color. Now I'm just going to update this a couple of times until it settles into a solution. And what you'll want to do, for example, with the small world topology, is to vary the number of, the amount of rewiring, and see what happens with the average time to the solution. So are nodes better able to solve when there are fewer or more of these rewired links, or is there a sweet spot in between? So let's see if we can answer this question. As the rewiring probabilities increase from 0 to 1, the following happens. The solution time decreases, the solution time increases, or the solution time initially decreases, then increases again. If you manage to get the model to run, what you should see is that when it's a regular lattice, the amount of time it takes for the solution to propagate all the way around is fairly long. As you add more edges, the solution time should drop, and then it increases again, interestingly enough, once you have many additional edges, potentially because that means that the problem itself is more difficult, because a node that has more neighbors has a tougher time figuring out what color to be. So just to recap, what we learned this week was that network topology can have a profound influence on the processes that occur on these networks. It can influence what state the nodes converge to. Will the whole network become infected or not? Will they adopt one opinion, or will many different opinions persist? And it can also affect how quickly that state is reached. What is the time to convergence? And we saw different behavior depending on what the process was. Was it just simple diffusion, or was it complex contagion? Was there an element of coordination or collective action? Were the nodes doing something else, for example, learning or innovating? And how did what their neighbors were doing influence their own development? And ultimately, how well did the network as a whole perform from the nodes making these individual yet interlinked actions? Hi, so here I am with Eric Sun of Facebook. The first question to you, Eric, is how did you come to do social network analysis for a living, and what does that entail here at
Okay,
Facebook?
so I've been at Facebook for about 4.5 years. I started as an intern on the data science team. So over the last 4.5 years, I've done pretty much everything related to data here. I first came here because I was an intern. I was in grad school in statistics, and I wanted to come to a place where I could have my hands on all the data I could ever want and more. So this was a natural place to do it, and I've been here ever since. So in the last 4.5 years, I've done everything related to data, from research and analysis to machine learning to building front-end products for users using our big data sets.
Cool. So specifically for this course, though, I'm trying to convince students that knowing about social networks and doing a little bit of analysis is useful. So, which, if any, of aspects of social network analysis have you found useful in your work?
So for my work, I would say that these days, building front-end products with data is one of my primary focuses, and especially now that we have this graph of on Facebook that we call the entities graph, which is everything on Facebook except for the users. So we're already doing pretty well at being like the social graph of people in the world, but we're not doing so well yet at modeling everything else. So I'm talking about the pages and the places people connect to specifically. So with this, the best way for us to scalably clean up and model this graph is to use crowdsourcing. And when we're developing crowdsourcing algorithms, it's a huge amount of social network analysis to figure out what kind of tasks to send users, what we can do to use social signals to improve our agreement metrics. For example, like how many yes votes do we need to how many yes votes or no votes do we need to accurately say that something is a good judgment or not, for example. We also use social network analysis to do a lot of things. For example, this paper I'm about to talk about, where, for example, using for search ranking, social signals is one of the big factors in search ranking.
Cool. So modeling not just the large social network, but the whole world.
Exactly.
Using social network analysis.
Exactly.
So without further ado, let's see if we can switch into slideshow mode. Okay, yeah, we're fine.
All right, so now I will talk about a paper that Jonathan Chang, another Facebooker, and I wrote last year on Facebook Places. So this is an example of how we use social network analysis to improve a specific product on Facebook, namely the Facebook Places service, search ranking, and crowdsourcing. So if you're not familiar with it, we have a lot of location-based services now on Facebook, similar to Foursquare. Gowalla, I guess, doesn't exist anymore, but these services all allow users to share their location to their friends. And there's a lot of factors that affect where these users check in, and the idea we had here when working on this paper was to see if we can figure out where people are going to go in the future. So there's a lot of pretty obvious implications for this. One is ad targeting. If we know where you're going to go in the future, maybe we can send you a coupon or do something else that will improve your user experience. If we suspect if we can suspect where you're going to go in the future, we can also use that to improve search ranking in your check-in flow, because maybe you can just press check-in, and then the place where we think you're about to go will just show up on the top. All right, so in order to do this prediction, we use social network analysis to extract a lot of features to use in machine learning. So, for example, we use previous check-ins that you have. We also use all the previous check-ins that your friends have done recently. And as a preliminary data analysis, we used an algorithm called LDA, latent Dirichlet allocation, to group related places. So here we consider, it's basically a topic modeling where you treat the users as terms, and the words in the places as the words in the document. And if you run this algorithm, then we quickly see that related places pop up very quickly. So here we tried running this algorithm on San Francisco, and when we ran this, some of the topics that popped up were these topics, topic 1, 2, and 3, where topic 1 looks like all places within the Castro district of San Francisco. Topic 2 looks like, I think that's places in the marina in San Francisco, and topic 3 are places that are not really in any specific geographical area, but rather these are all like Asian themed places within San Francisco. So these are people who check into any of these places are highly likely to check into other places in this group. So it is pretty interesting to see what kind of data pops up just from using a little bit of social network analysis and some unsupervised learning. So just to show some more pretty pictures, so some of the other features we used around predicting check-ins was first demographics. So here in this heat map, lighter areas mean more check-in activity. So if you're familiar with San Francisco, this is a map of the various neighborhoods of San Francisco, and we see that males typically check into the Castro district, which is a very gay-heavy area of San Francisco, whereas the females tend to check in the financial district in do you know what that neighborhood is? North Beach, I think, where a lot of the clubs are, and therefore it's pretty striking how different males and females use Facebook Places. There's also temporal features. So we realized that most of the morning check-ins are around like the financial district, where people are just getting to work and checking in. People don't check in nearly as much in the morning as at night on the right side of the screen, where tons of check-in activity are to nightclubs and areas where nightlife is really big in San Francisco. So the next step is to actually predict check-ins. So we do the standard thing in machine learning where we hold out some check-ins and run a regression to try and predict where someone is going to check in next using all these features that I just mentioned. And it turns out we can actually do pretty well. So if we want a recall of 60%, we can actually predict with 90% precision the next place that a given user is going to check in, which was pretty surprising to us, because that it means we're doing pretty well with a large percentage of our data. Not surprisingly, predicting whether someone will comment on this check-in is a lot more difficult, because that's just a lot of noise and a lot of just a lot more randomness. So here we see that with a 60% recall rate, we can only predict with about 6% precision. So this is basically just noise, which was not too surprising. However, we do see there are patterns. So we did notice that responses are much more likely when someone checks in far from your usual location. This is typically when I am going on vacation and I check into, let's say, Hawaii, whereas normally I live in San Francisco. So my friends are much more likely to comment naturally if I'm on vacation in Hawaii. So here the blue line is is likes, and the red line is comments, I believe. And the x-axis is the log of distance in kilometers. So the farther away you go, the more feedback you get on your check-ins. Not surprisingly, we also get a lot of boost when someone checks in close to the commenter / liker. So if I live in San Francisco and I suddenly go to, let's say, Berkeley, and I'm now very close to my friend who lives at Berkeley, then they are also much more likely to comment or like my post. This is also not very surprising, and it's good to see these kinds of things borne out in the data. So whenever we're doing these kinds of analyses, social network analysis in particular, or otherwise, it's really important to do enough just background summary statistics and some basic plots to make sure you understand your data, and to make sure that your data is sane and correct, and you can figure out if there's any outliers you need to get rid of or anything else you need to clean up before diving into anything deeper. All right, so just to talk about some of these applications. So we have this graph, and right now the big focus on our team is to use crowdsourcing to improve the graph of places by adding metadata and removing duplicates. So these are some screenshots of some units we have on our homepage, where we ask users, like, what kind of place is this cafe in Seattle? We also have a flow where users can add data like categories, name, address, city, town, to any place that is not owned, and help us fill out our graph. So there's a lot of really interesting work being done in crowdsourcing in particular, because as I touched on earlier, we want to only accept suggestions that are good. And how do we figure out what's actually good is that we do a lot of analysis to use lots of social features around demographics, around whether you've interacted with this place, whether your friends have interacted with this place, to try and get a sense of whether you are likely to provide good feedback. Because at Facebook scale, we have users of all kinds. We have spammers, we have people who just don't know what they're doing, people who are like very young. 13-year-old girls generally don't provide really good crowdsourcing suggestions, we found. But using these social features, we actually can provide some meaningful lift and figure out what crowdsourcing, how to use social signals to improve our crowdsourcing. So some other applications which I touched on earlier is just better ranking for Facebook places, more ad targeting, and also recommending places you might go in the future. So these are all areas that we're actively working on.
Cool. All right. So thanks, Eric. I think that was a nice broader introduction to data issues and useful applications. So thanks.
Sure. Thanks.